All right, so let's see, what did we say? We said x bar equal 9, 9 to 9. We said that sigma, which we have to have, equals 2. We said that n equal 49. Now what we need is z alpha halves for a 99% confidence interval. Well, I just showed you. Oh, let's go to this guy. Look at that. It's sitting right in front of us. Isn't that lovely? 2.575. So that's my Z alpha. We could show that if we had to. Remember, I showed you this. If I go up here and I find 0.005, let's see if we can find it. Oh, look, they've done it for us. It's halfway between 0.0051 and 0.0049, which is negative 2.575 because of the symmetric property of the normal distribution. We can write it both ways, so I'm simply going to write it as positive 2.575. Because remember, in the confidence interval, when we build that sucker out, we end up with that plus and minus, so it's all taken care of. All right, so here we go. Remember, it's x bar minus z alpha halves times sigma over root n comma x bar plus z. I'm kind of breaking my rules about fractions here. I usually don't build them on diagonals, but that is what it is. That's a times divided by root n, and then plug and chug. So 999, simple formulaic, right? 2.575 times, what is that, 2 over root 49 and 99 plus 2.575 times 2 over root 49. And let's see what we get. I need to speak some languages of mathematics here, so bear with me. I've already got most of this in my calculator, so I'm going to turn this into a 2.57, insert 5. I want to hit myself and enter it, and I end up with, over here on the right, I end up with 999.74 when I add, and when I subtract, I get 998.26. 998.26. Now, let's compare that real quick. Let's look what happens if we want to be 99% confident. All right, now let's talk about this theoretically for a sec, just so we can get our brain wrapped around this. Okay, I'm going to change colors. When it was 95%, think about what happens on the normal, right? I need to pick up 95% of all of the data. If I want to go to 99%, I have to be more confident. So I have to carve out more. So I get 0.99. So my interval had better be bigger because I'm simply grabbing more of the normal curve. So look, let's see if it is. 998.26. Over here it was 998.4. It was also 999.56 over here. And over here, it's 999.79. So we actually did get this sort of stretching effect because we wanted to be really, really confident. And look at what happened. Notice that our mu, which the claim by the Pepsi company, which again, I made this up. I want to indemnify myself against any liability from the Pepsi company. Made up, Pepsi. Don't sue me or have me killed. The claim by them is that it's a 1 liter bottle or 1,000 milliliters. And guess what? It ain't in that interval. Something's wrong. Their claim appears to be incorrect. Now, there is a far more formal set of steps that we have to go through to be able to do this, to be able to actually to test the claim. That's called hypothesis testing, and we'll go over that in the next chapter. But I think you're starting to see how this works out, and we'll play with these a whole bunch more. All right? Hey, guess what? That is building a confidence interval. Now, remember before how we wanted to figure out how big n should be? And we did that for proportions. It's sitting back here. If I stumble back over here, let's see, where are my terrible, oh, we got 2 more back, don't we? Remember these guys right here, these formulas? This is when the prior research was done. This is with no prior research, and these were the 2 formulas. It would be nice to be able to figure out in exactly the same way how many Pepsi bottles I should pick out to be 95% confident in my confidence interval. Because, I don't know, maybe I'm off. Think about this. If I've done no prior research and I want to be able to figure out what n is, or how many Pepsi bottles I should go in to be certain, then that's a good piece of information. So watch how this works. Remember, this guy right here is my error. This guy right here is my error. It's how far off my point estimate is going to be to create the confidence interval so that I'm 99% confident that the mean is in it, the true parameter is in that interval, right? Remember, this guy was there. So if I use simple algebra, if E equals Z alpha halves, I'm going to start obeying my own laws here, times sigma over root n, and I'm looking for how big I want my sample to be before having done any research. Watch, it's super easy. I know that root n equals Z alpha halves times sigma over the error, which I'm going to choose. I'll show you how to do that in just a sec, which implies that n equals Z alpha halves times sigma over the error, and then I just square this whole sucker. No brainer. All right? All I did was algebra. So let's do this just for fun. I want to know how big of a sample to pick if I want to be 95% confident. All right? So again, I'm going to build a 95% confidence interval down the road, but for now, I just need to know how big my sample size should be to feel that I've done it confidently. Well, let's look at the formula. What do I need to know? I need to know the population standard deviation. Without that, things change drastically, which we'll talk about here in just a sec. So in this case, let's see, for the Pepsi bottles, I know that sigma was 2. I know that Z alpha halves, if I'm going to be 95% confident, is 1.96. And let's see, what's my error going to be? Well, think about that. If I'm 95% confident, then my error, the amount that I'm off on either side, the error is going to be what? What would it be? Is it going to be 0.025? Is it going to be 0.05? I mean, that's something that's really, really important. So think about that for just a sec. Okay. Hopefully you gave that just a gander. Now, the difference between when we're doing confidence intervals around the mean and when we're doing them around the proportion, remember, when we're doing around proportions, this error is going to be a certain percentage point. But when we're doing it around the mean, in this case, it's going to be in the same units as our average. Remember, X bar was 99 mLs, right? So our error isn't going to be a percentage that we're off. It's going to be in milliliters. All right? It's going to be in the same units as our data is in. Think about it that way. So we get to build this. All right? Now, again, we're talking about an error measurement that is different. It's fundamentally different than it is with population proportions, with using confidence intervals to approximate those. Because now we're talking about the way in which the data is collected. It doesn't have anything to do with proportions. It has to do with something that has units attached. So let's say that I'm going to build a 95% confidence interval around, again, the Pepsi problem. I've done no prior research, so let's make this go away. All right, I'm just like, well, let's see, what the heck. I want to be off by 1 milliliter. Notice this formula has no X bar in it because the error statement has no X bar in it. I want to be off by 1 milliliter. And this thing's going to tell me how many I gotta collect. So nothing to it. You ready? I know that N is going to equal 1.96 times 2 divided by 1 milliliter. Clearly this is overly simplified. And this whole thing is going to be squared. All right? So if I stumble in, let's see. I'm sorry, you guys. I'm going to grab my calculator here. 1.96 times 2 squared. I have to get 15.366, which clearly I can't collect 15.366 bottles of Pepsi, so I'm going to collect 16. That tells me I don't even have to grab, remember over here, to build my 95% confidence interval, I grab 49. I really, as long as the standard deviation is known, that's so key. I want to emphasize that as often as I can. I really only needed to grab 16. With this specific error, I get to pick the error before I build the confidence interval. Okay? Now, let's talk about, hopefully, that's a relatively straightforward process. Let's talk about our assumptions. And by the way, I am not going to make you memorize these formulas. I'm going to give you a formula sheet on any exams that we take. In fact, we're going to, hopefully by now you see that we've posted formulas all over the classroom, so they're going to be sitting there for you. Let's talk about our assumptions. The assumptions, of course, is that the sample is random. It's randomly collected. Without randomization, all of statistics falls apart. You have to randomly collect your data. Hopefully that assumption is always in the back of your brain. Well, we have to collect it randomly. We have to collect it randomly. Remember way back in chapter, I forget what it was, 1 or 2, it was like randomized designs are always the best. The other is that to be able to do this, sigma, whoops, I don't know why I use an equal sign, sigma is known. It has to be. Not S, but sigma. All right? Hey, that takes care of it. There's nothing to it. We've got ourselves the ability to build a confidence interval around mu. We've got a wonderful way to figure out, given a known error, how big of a sample that we should collect to make sure that we get enough data to be able to confidently build that interval. No pun intended. All right, cool. We'll meet you in the next